Quote, "There is nothing more practical than a good theory." Unquote. Ludwig Boltzmann. Thank you to those who are joining me here today. We're going to be talking about the emergence of life at alkaline hydrothermal vents. And I'm privileged to be joined by Dr. Michael Russell, who's joined me for conversation on this topic. I want to say before we begin that this interview is going to be a bit unconventional. I'm basically asking Dr. Russell for his responses to various things that have been discussed in the literature. And as such, I'm going to be quoting sometimes somewhat extensively from some of these papers. And so for that, I beg Dr. Russell's and our listeners' indulgence. With that said, I want to introduce my guest today. Dr. Michael Russell is a geologist who's been a pioneer researcher on the question of the emergence of life. He worked as a mineral exploration geologist in the Solomon Islands and Canada, and received his PhD in geochemistry at the University of Durham. Besides holding teaching posts at institutions such as the University of Glasgow, Dr. Russell was a NASA Senior Research Fellow and then a Principal Scientist at the Jet Propulsion Laboratory, California Institute of Technology, from 2006 until 2019, and a member of the NASA Astrobiology Institute until 2021. In June of 2009, Dr. Russell was awarded the William Smith Medal for his lifetime contributions to applied geology, and in 2018 was awarded a very well-deserved NASA's Exceptional Scientific Achievement Medal for his research into the emergence of life. Dr. Michael Russell, thank you very much for joining me here today.
It's a pleasure, Drayce. I look forward to the questions.
Thank you. To begin, just to get a little bit of autobiography about yourself, I wanted to ask you, what was it that first sparked your interest in this subject of the emergence of life? Was it the discovery of black smokers that was like the initial catalyst that led you to pursue your own theory? Or had you been considering this question at an even earlier point in time?
No, I hadn't. And the black smoker reference is a very good one, but not directly, because what we saw, I happen to know the people who've discovered the black smokers, and they really were a wonderful couple of geologists, that, as I understand it, Jack Corliss and John Edmund. And they discovered these chimneys. They'd actually predicted that they were going to discover these big black smokers, and they were discovered in the Pacific. And I happened to see a good video of those. And so when I was looking at my own mineral deposits, which are 350 million years old, with my students in Ireland, we always thought these mineral deposits were laid down on the seafloor from hot springs. So I began to think, right, let's look for hydrothermal chimneys. Now, there was a paradox to this, because I happened to be working with students, and I said to the students, there should be chimneys here, hydrothermal chimneys here. One of my students said, what would they look like, Mike? And I took the pen top off my pen, and I showed it to them like this. And I said, well, it'll be made like this, but they're that size, and they'd be made of iron pyrites. And my student said, well, Michael, I've got a million of those. Well, we didn't have a million of them, but within 5 or 10 minutes, we'd collected quite a few. And that got us started in being interested, really. That was in about 1980, I think. And then what happened next was that we, as often happens in science, our publications on this idea were met with derision, because our little black smokers were so small compared to the very big ones. And so we felt a bit disenchanted with our discovery. But what happened next was that I was playing chemical gardens with my children, just to keep them off the street, basically, and where you put various sodium silicate solution into crystal with cobalt chloride or something. They make these beautiful spires. They're called chemical gardens, and I think I've got a picture of them somewhere, I hope, in this program. But what happened was that I left, went to work, and came back, and my young son, 11-year-old Andrew, had taken my chemical gardens, which I'd put on the mantelpiece because I thought I was so proud of them, and he took them into the bathroom and started taking them apart. And I was a little bit upset about this, and also because I'd been cooking supper, and I remember saying to Andrew, it's supper time, come out there. There was no answer, and then suddenly he yelled out, "Hey, Dad, these things are hollow." And I thought, wow, of course, what we're looking at is natural chemical gardens. So then I took this idea into the lab next day to see my long-time, very good, wonderful collaborator called Alan Hall. And we talked about it over coffee. And one of us said, maybe this could be significant to the origin of life, because after all, these crystal gardens are made of membranes, and the particular ones we were looking at were iron sulfide membranes. And I did know that iron, as everybody knows, that iron is very, very important to life. So that's how we got started. But then I kind of left things. I was very busy with lots of other things to do as professor in Glasgow, and I left that for about 3 or 4 or 5 years, perhaps more. And then finally, somebody called Stanley Miller, who was very famous for a hypothesis of the origin of life, whereby lightning was supposed to make organic molecules from what's called a reduced atmosphere. And he'd written in to Nature to say it was nonsense that life could have started at hot springs because they were too hot. Well, I hadn't realized it was the Stanley Miller, but I replied and said, well, that's true of most hot springs, but our hot springs happen to be much lower temperature and is much smaller. And I got so many requests for that paper that I got quite excited. And I thought, right, perhaps we should get back into working on the origin of life. And it was only after a while I realized that it was an emergent structure, that life is an emergent structure. You can't have things just appearing. You don't have immaculate conceptions. You have things actually, one thing being derived from another, from another, from another. So, for example, children don't just originate, they are born. And of course, there was conception that went into that. There was a whole history. And we like to think about the history that went into the emergence of life. So that's where we are. That's how we got started.
Thank you very much for that, Dr. Russell. I'm going to be changing our screen now and bringing up your slide presentation as we continue our discussion. So I'm going to switch this over and pull this up. Just let me know if there are any problems in seeing this. Can you see this clearly?
Great, perfect. Well, that's just the slide I wanted, so thank you. So yes, on the left-hand side, top left here, are the chemical gardens I made. Actually, they are the chemical gardens I made with my children. You're looking at something about 6 inches across and about 5 inches high. And there's an equation there to show you how easily they are to be made. So you can take a cobalt chloride crystal, it's what's called a hydrated crystal, you drop it in, it dehydrates and kind of expands and makes these beautiful spires in sodium silicate. So down to the bottom right, you've got something that looks very similar. But the first springs we found, the first what we thought were black smokers on the top right here, the hydrothermal iron sulfide chimneys from silver mines. And you can see they look rather like black smokers, but they are very tiny. We published that in 1983. And you can see the similarity down to the bottom left with the black smokers. And one of my excuses at that time was there was no scale on those black smokers. So I didn't know how big they were. And also I didn't know they were vandalized. And in fact, the top had been knocked off by the submarine. So they did look very similar to us, but they are very much bigger, I have to say. And in the middle, now down the bottom, we've got some actual iron sulfide chemical gardens that we grew when we were trying to show that maybe life started with using iron sulfide chemical gardens. And as I say, I returned to the bottom right-hand structure, which we found in the Irish deposits, about 350 million years old. And you can see, I think, that make beautiful natural chemical gardens. And if you look very carefully, they've got a central channel to them, or some of them got a central channel, showing that actually liquid did come up the center, and they grew in that kind of way. And we felt maybe they're the first membranes of life.
So your views have undergone some modifications over the course of the last few decades, and I wanted to ask you about this. I wanted to ask you if you could share with us your reasoning regarding some of these changes you've gone into so far, the transition from discovering black smokers to now alkaline vents. But for example, could you explain the notions of negentropy trapping that you discussed previously versus what you favor now in terms of entropy disproportionation, and go into why you made the transition from one to the other? Also, I was interested in the same for your transition from iron monosulfide bubbles to Fujirite, as you explained in your 2018 article on green rust.
Okay, well, being a scientist is being a research worker. I was a geologist. I knew some chemistry and geochemistry. But what, of course, if you follow a dream, as you know yourself, Drayce, you get taken up by different directions. And therefore, I found myself having to learn a whole lot of new areas of science. And of course, that brings you to different conclusions. And as you basically, you evolve, your mind evolves, and you do what you think is next. So the thing is, you don't kind of stick around and stick with what you're doing. You say, right, that's very interesting, but maybe I could develop that. And so we started off with this low entropy or neg entropy idea, because I think nearly everybody who works on the emergence of life, or even those that work on what they call the origin of life, is very familiar with Schrödinger, his 1944 book, What is Life? And I think it is I read it every now and then, and every time I read it, there's something new and different. It's very engaging, very easily written. So what he said is that basically he was following Ludwig Boltzmann, that I noticed you used in your first quote. To me, he is the greatest scientist, one of the greatest scientists of all time. And Schrödinger was, of course, not far behind, and he was a disciple of Boltzmann. And he used Boltzmann's approach to entropy, and he said, what you need is, life is very low entropy. It's incredibly well organized. And yet what the universe does is to generate more and more entropy. It makes the universe disorganized. The universe breaks its plates. It's breaking things all the time. It's very hard to put things together, but it's very easy to break them. But breaking them needs actually a very well organized system. So that's where the idea of neg entropy came in, that life is extremely well organized. So we have to have a very, very low entropy environment. To put it another way, you have to have a situation where the degrees of freedom are extremely limited. You've got a little bit of possibility of exploration, but generally very limited. You can't. This is why I'm not very keen on the pond, the RNA pond, because there's no limits to that. But you'll know that if you want to do anything, there's a lot of limits to it. What's that famous author about the 10,000 hours? You want to be good at something, that's 10,000 hours. That's very probably in a closed room or some such. So that's low entropy environment. But of course, all the waste involved is the high entropy. And this is the real kind of change. It's not much of a change between entropy disproportionation. What I think is that you have to get very low entropy system so that you get very large amount of entropy generated, because the universe is concerned on making a mess of itself. Believe it or not, it just wants to be, it was born so far from equilibrium, and it just wants to relax closer, and the way it does it is through things like whirlwinds and so forth, and volcanoes. That's actually brings the universe to much more closer to equilibrium, but it does by actually having very low equilibrium systems, disproportionation generators that can lower the entropy inside something so that more and more entropy is made outside. So, for example, in ordinary life, you can think of the artist's studio. What is the artist studio? The artist studio is a painting or two or three paintings on easels, but I'm sure that the floor is covered with rejected bits of art and old brushes and bits of paint. It's always a mess. And that's the entropy from the low entropy of the actual painting.
Thank you. And So I'd like to turn at this point to some of the criticisms of your theory and to consider your responses to them. There have been some recent arguments claiming that proton gradients at alkaline vents, in fact, only provide a fraction of the required energy to power the emergence of life. For example, in a recent exchange between Origins researcher Jeremy England and Brian Miller of the Discovery Institute, Miller claims the following, and if you'll indulge me, I have to go through this quote. So he says, quote, "The power production density of the simplest known cell for only maintenance is on the order of 100,000 μW per G. A leading proposal for energy production centers on proton gradients in hydrothermal vents. Experimental simulations of vents under ideal conditions only generate small quantities of possible precursors to life's building blocks, and the corresponding power production density is on the order of 0.001 μW per G. This quantity is considerably greater than what could practically be transferred to any stage of abiogenesis, yet it is still 8 orders of magnitude too small even to prevent a protocell from quickly degrading back to simple, low-energy molecules." And for this, Miller tries to raise some support for his claim, and he quotes from the article Hershey et al. 2016, their use of the benchtop reactor in order to justify his numbers. In a footnote, he writes, "The reactor simulation generated an approximately 20 nm concentration of formaldehyde from hydrogen and carbon dioxide in 10 minutes in an approximately 1 liter vessel, and the entire reaction corresponds to 2 electrons, n equals 2, increasing in reduction potential by less than 200 MV. The reduction potential can be converted to the free energy change for the production of 1 mole of formaldehyde using a delta G equals NFE. The corresponding power generation density is on the order of 0.001 μW per G," unquote. So how do you respond to this claim being put forward that the energy production, the power production at alkaline hydrothermal vents is too small?
I think, well, I think that that Jeremy England takes the wrong points from a theory of thermodynamics. What I'd say is that we know that each cell uses about 1 million electrons a second just to get by. So that's a lot of electrons. So I recognize that. But also we know that not only does it have electrons, but protons are significant. In fact, it's what's called the proton motive force. Now, the proton motive force is involved in making what's called ATP, adenosine triphosphate, but it's also significant in actually, for example, generating, as we've heard, organic molecules, and, for example, making using electrons from using a proton gradient of something that is equivalent to 200 millivolts. Now, at our vents, we have the equivalent of proton motive force of 300 millivolts. That is because there's 5 units of pH difference between one side and the other. Now, you could say that's just me whistling a different kind of tune, but not necessarily upstaging Jeremy England, except that now, just very recently, Hudson and somebody called Jerry, what's his name? Hudson, Reuben Hudson, and the people from Nick Lane's lab and various other people have actually shown that they can take an iron sulfide membrane, such as we first suggested, put a pH gradient of just over 200 millivolts through it, or shall we say 3 pH units, and they actually do reduce carbon dioxide to formate. I'm not so keen on the formaldehyde story, but that is a kind of another story. But formate is the kind of basic organic molecule. And from there, you can go into acetate and so on. So I think that it's all very well to say that from a theoretical point of view, but we can show practically in the lab that the hydrothermal vent will satisfy what's required for what's called autotrophic metabolism. That is a metabolism that starts with carbon dioxide and electrons from hydrogen and makes, with help from other materials, makes life as we know it. But of course, life is extremely well organized. So it's not, perhaps something to say about this, it's not chemistry. It's or not just chemistry. It's actually a kind of nano engineering that we have to think about. Enzymes aren't catalysts or merely catalysts. They actually have motion to them. And I'll get back to this kind of motion. But here's an example up here of, for example, far from equilibrium systems, which we well know of. So, for example, making a radio is making something that's very difficult from scratch. It's something that doesn't occur in the universe unless we make one. Making the sandcastle on the right is kind of pretty hard as well, and that's should be proud of. And the nearest thing to equilibrium there is the pool, which is just kind of lying there with a little bit of wind happening to it. But the big thing there is this great, wonderful roller coaster. And I think most people think that life is just a matter of chemically going downhill, okay? That you just go down that hill, but in fact, you need an engine to get there. And you need an engine that's also a ratchet. So every time it makes a little jump forward, it stops itself going back, jumps forward and stops going back, and so forth. That's how an enzyme works as well. It goes a little bit forward, driven by the kind of small change, for example, of electrons and protons. One of the great ideas that Nick Lane realized, and that is you can make up, shall we say, large quantities, the kind that Jeremy England wants, by doing it a bit at a time. Kind of into a piggy bank, so to speak. Anyway, once you've got up to the top there, then you can go down the hill on that roller coaster, and off you go until you've run out of all that free energy that was given because of the engine to start with. So that's very similar to how life works. And on the right-hand side here, I've got this idea of what we call entropy disproportionation, because here's the order creation in this. You were asking about foods, right? Well, we think this is a much better mineral, or not the only mineral anyway, at the alkaline vent, but it's a kind of layered mineral, and it's very, very small, very thin layers in it with a minor amount of water. And we think that the water goes through there and with hydrogen and carbon dioxide and so forth. And it's the electrons and the protons that actually help to reduce these carbon dioxide to the organic molecules we're talking about. And the actual disproportionation is that the part where the arrows are going through, that's where the low entropy is. But the waste is the high entropy. And in fact, it's always rather hard for people to realize this, but it's the waste that drives us. It's actually going to the toilet that drives us. It's not breakfast so much. And it's rather like the point about that it's the engine it's the exhaust that drives your car. If you can't have an exhaust, if you don't fire off in the engine, nothing happens. Doesn't matter how much petrol you put in the car, it won't go unless you light up the cylinders and allow the exhaust. It's the exhaust. And when you come to a rocket, it's very much more obvious because the rockets are driven by the exhaust.
Yes, you mentioned in a previous conversation, was it a Monty Python movie where they put, what is it, like a banana in the exhaust pipe?
Yes, it was Beverly Hill Cops.
Oh, that's right, yes.
And who's a famous actor. Well, he's the guy from Chicago. He's a smart guy from Chicago. And the Beverly Hill Cops from near Los Angeles are kind of pretty dozy crowd. And he's getting chased by these guys. So he goes into a store. Eddie Murphy goes into a store, gets some bananas and sticks the bananas up the pipe, the exhaust pipe of this Beverly Hill Cops. So when he takes off, they can't follow because there's no exhaust. In fact, of course, a spoiler to this is that people say, well, actually, what happens is the bananas pop out anyway, but they're still driven out by the exhaust.
Very well. I have to add a quick comment here that I thought it was very important when I found out that the benchtop reactor that's used in the Hershey et al. Paper, it was later abandoned by the researchers, specifically because they could not get it to operate at full capacity. And several of the researchers have commented on this by now. Lane has mentioned it, as well as Dr. Camp-Ruby Casas. So the quote that I gave describes using the figures derived from the benchtop reactor as ideal conditions to test vent power production. But given the fact that it's deriving these figures from the benchtop reactor that was later abandoned precisely because it could not operate at full capacity, I don't think describing this as ideal conditions is appropriate. You've referenced me to Yamamoto 2013, where they've actually gone out to extant hydrothermal vents today in the ocean. And the power production that they're directly measuring from these vents today is much higher. Isn't that correct?
That's perfectly correct. And I think it's fair to say it was abandoned, but it was a necessary experiment of Hershey because you just have to start somewhere and you hope each time to improve. And they have really improved their rigs now, I can tell you, in that lab, in Nick Lane's lab at University College London. And they've also using different techniques, this microfluidics technique, which I think has got a huge amount of future because you can pressurize the reactor to similar depth to the deep sea floor, and you can put the temperature and the different pH and what's called the redox or the oxidation reduction states in this kind of what's called a microreactor or a microfluidic reactor. So I think it was a necessary stage, and in fact, what they're doing now, and I think I can fairly say that I think these papers are coming out pretty soon. And that is that they are being much more successful than they were. If I were to make one comment on this, I'm a little bit uneasy about formaldehyde because formaldehyde is everywhere. It's very easy to find formaldehyde in your rooms, school rooms, and so forth. It's unfortunately everywhere as a pollutant, so it's often rather difficult to analyze for, and it's extreme, and yet it's extremely unstable. So I'm not sure that life would have stuck around with formaldehyde for more than, shall we say, a nanosecond or two. But nevertheless, no, I think that what they're doing, what Ruben Hudson is doing in the United States, and what Nick Laden's doing, what Laurie Barge is doing, and so on, is really, and Steinbach's doing in Florida. That's really, it's the name of the game. It's what to do, and I take my hat off to them. I would love to have done it myself.
Thank you, Dr. Russell. One of the most influential questions of alkaline hydrothermal vent theory comes from a series of papers by Dr. J. Boz Jackson in a series of articles that he wrote in the late 2010s. And on the matter of McKenna-White and Fujirite, he writes the following, which I'd like to get your response to. He writes, quote, "The mechanisms of the modern day H plus pyrophosphate synthase and H plus ATP synthase centrally require extensive and complex alterations in protein." Oh, hold on here.
In proton.
Yes, I'm sorry, proton. But let me see. Okay, yes, proton conformation to affect coupling between the hydration-dehydration chemistry and transmembrane proton translocation. These conformational changes taking place across the protein molecule are essential both to gate steps in the reaction and to support changes in substrate binding energy. It is extremely difficult, if not impossible, to envisage how early non-protein inorganic versions of these enzymes could have operated without equivalent structural alterations. Speculations that, quote, positive redox polaron waves augmented by the proton gradient, unquote, and complexes of brucite, McKenna-White, and Fujirite-like minerals can serve as a peristaltic drive of phosphate molecules into low entropy two-dimensional space where they can condense to pyrophosphate are splendidly imaginative, but not in the least supported by observations in the laboratory, end quote. And by contrast, Lane's article on proton gradients in 2017 answering Dr. Jackson suggests that at the emergence of life, molecular engines may have been unnecessary. So I know you've already gone into this a little bit, but how would you respond to the critique of Jackson and the conversation that he's been having with Dr. Lane?
Well, one of the problems that the emergence of life is what I would call a hyper object. It's incredibly complicated, and you have to know nanotechnology, chemistry, geophysics, communication theory, coding. I mean, I don't know what I don't need to know, frankly, in terms of the emergence of life. But one thing everybody seems to ignore is geology. And yet, of course, the evolution was brought about by a geologist, and his name was Charles Darwin. And he really was a geologist. He was secretary of the Geological Society of London. You need to understand geology. And if you don't understand geology, or at least refer to it, or at least have some empathy with it, or at least know geologists, then you really can't start to criticize, I think, this kind of system. One of the things I'd point out is there was no suggestion, we've never made a suggestion that we need to start with ATPase. That would be ridiculous. Of course, it's not the case, but evolution takes care of a little bit at a time of actually making things better, going from a rolling a log to a wheel, to a horse and cart, to an engine, and so on. You know, so we don't. Of course, we didn't start. We like to think we've got a wheel. The origin of the wheel, the analogy would be the origin of the wheel. So, and also we can say that what Jackson said is just refuted by the fact that we can actually make, or it can be made, CO2 can be reduced by hydrogen in one of these systems. And I think that the next, of course, I will make one big point here to kind of make it clear about the issue, and that is, yes, we need to make peptides. We need to make these, shall we say, proteins that can change their conformation and so forth, wriggle around, if you like, to become little engines. But green rust, this mineral on the right-hand side in this picture, that can wriggle around. It makes a difference if you oxidize or reduce it. And it either squashes things together or pulls things apart. So I think that it was an interesting interaction. I think that Nick Lane actually dealt with it in a masterly way. But no, I would still think we need to have some pyrophosphate, and we argue, and we know you can make pyrophosphate out of aspartate phosphate and monophosphate. That's Laurie Barge's work. So we think it's just a matter of time until we make pyrophosphate in one of these systems, and then help to perhaps to make peptides. And peptides is the next big job. But somebody just this moment, and I can't see it right now, and his name is Cook, has just sent me a paper that's just come out in PNAS on how to make peptides, that is putting amino acids together in very small amounts of water. So in the middle of these green rusts, you have very small amounts of water. So we like to think it's just a matter of time. And that, of course, there's a whole group of people working on the emergence of life, but most people do not worry about the entropy aspect. But this is what we will emphasize. That's why we don't like the warm little pond idea, the RNA pond. We think it's absolutely hopeless. And I could tell you more about that if you wish, but probably you have another question.
Yes, we'll definitely be getting to that because Dr. Deemer has tried to address non-equilibrium thermodynamics at his hot springs. And so I do have a question about that we'll get to momentarily. In the meantime, to continue a little bit with Jackson, he had a follow-up article, Ancient Living Organisms Escaping from or Imprisoned in the Vents, published in 2017. And he focuses on the frequently asked question of how our pioneer organism could have escaped from the vents. In the abstract of his paper, he writes, "We point out that it may have been impossible for organisms to have acquired membrane-located proton or sodium ion pumps to replace the natural pH gradient and independently to have driven essential molecular machines such as the ATP synthase. The volumes of the ocean and of the vent fluids were too large for a membrane-located pump to have generated a significant ion concentration gradient. We conclude that ancient organisms utilizing a natural pH gradient would have been imprisoned in the vents, unable to escape and become free living." What do you make of Jackson's argument in this paper?
Well, I mean, it wasn't only ignorant, it was also unscholarly, because we happened to have published a paper in 2006 that itemized exactly how the first organisms would have left the vent. And of course, they would have left down into what's called the deep biosphere. They wouldn't have gone in. Of course, the ocean was a desert. Of course, they wouldn't go into the ocean, but they would go into the deep biosphere where the geochemical similarities are there, although they're in much reduced energy quotients, if you like. So, but nevertheless, they are there. And so I think that the first bugs that developed an alkaline vent would easily live in the deep biosphere. And as you probably know, much of life is still living in the deep biosphere. So, that is down below the ocean floor or down below the land surfaces where there's billions upon billions of bugs. So it's no big issue to get away from the vent. Just go down, not up.
And when they go down, they're surviving off of materials such as like methane. Is that correct?
Methane, hydrogen, carbon dioxide, phosphate, the nickel and the iron and so forth that's in the groundwaters. So I mean, there's a lot of problems to be addressed in the emergence of life, but Jackson's was not one of them that really made any. Well, it didn't even change our minds, because we know that, for example, you get, as Nick Lane has pointed out, in these micro reactors, you get membranes down to about. And also, Laurie Barge has shown this. You get membranes down to about 20 nanometers. So that's beginning to becoming in the same magnitude as living membranes using lipids. So I think there's I don't feel threatened by that.
And just to ask, because in your 1990s articles, you emphasize like the fact that these vents break down very slowly. And so in terms of the idea of like incurring selection for a self-sufficient pH gradient, the slow breakdown of the vents, as well as like the gradual drifting away from the main source of the pH gradient provided by the vents, would you endorse those considerations as ways in which the pioneer organism develops its own pH gradient?
I think it's a great question. One of the things a geologist has to get used to is scale. So we geologists, because of microscopy and because they're interested generally into astrobiology and so forth, they have to think of scales right from the very, very small to the very, very large. And I think that in this case, the vent would last. For example, we know that one of these alkaline vents that was discovered, for example, we predicted the discovery of Lost City, and 10 years later, this alkaline vent in the Atlantic was discovered, and it lasts for 100,000 years. It's recognized using uranium isotopes. Now, 100,000 years is 10 to the 20 or 10 to the 21 nanoseconds. It's a gigantic amount of time, because life works on the nanoseconds. So to my mind, 100 years would be well in excess of what's required for life to emerge. The idea that life needs a lot of time to emerge is just not true. It would emerge quickly on the tour. It's basically, it gets to the tipping point and suddenly it's alive. And of course, mostly it would fail, as most life does today. I'm fond of pointing out that the Darwinistic term, the survival of the fittest, is a very poor term. It's the law of natural rejection. Most things are rejected. Yes, of course, you go to most of these vents and it wouldn't work. But there were billions of these millions of the places to go to over 500 million years, and billions upon billions upon billions of these crystals. So I don't see any issue with that at all.
Very well. A last follow-up question that I have for you on this, because you're emphasizing how quickly it can emerge. And there's a lot of conversation in online communities about the capacity of scientists to one day synthesize life in a laboratory experiment. How do you feel about the prospects of us being able to do that sometime in the future?
Well, I know that many people are saying they're going to be doing that. I think I first heard of it in about 2005, and it was going to take them 3 years. And I think ever since it's going to be taking just another 3 years. And I read a paper yesterday which said, of course, we'll probably do it soon. You know, people think it's difficult, but when we've done it, people will say, well, what's so difficult about that? I think it's going to be extremely difficult, but it's possible. But it won't tell us anything about how life started, because what these people are doing they're taking bits and pieces of what we know about life and trying to stick it together. Whereas I'm interested in how did life first emerge, and life's first emergence would not have been recognizable. It probably wouldn't have any DNA, or it would have different kind of codings. Well, it would have a coding system, and it would eventually become RNA and DNA, but not immediately. So so I'm kind of completely on the other page to these people that try to make life in the lab. My job is not to make life in the lab. It's to show that the emergence of life is a possible natural event that you'd get in the universe anywhere where you have an Earth-like planet.
Very well. Yeah, I'm glad you said that. That's actually been the sentiment that I've been arguing for. So I'm glad to have some support from you on that one. I wanted to move on here to Leslie Orgel. He had a very influential paper published in 2008 on the implausibility of metabolic cycles on the prebiotic Earth. There, he's mostly concerned about autocatalysis and these kind of metabolic cycles in terms of their inhibition by side reactions. And he's also highly skeptical that you would have all of this materials being available in one single environment. So I was wondering if you could speak to any thoughts you might have about Orgel's criticisms about a metabolism-first approach to the emergence of life, and about some of the advancements made on the topics of autocatalysis and metabolism, protometabolism, since Orgel first published his paper.
Well, I think that he was in the RNA world. He was pretty ignorant of most aspects of geology, and what he wrote is completely out of date, and it wasn't that good then, to my mind. So it's never been a particular worry for me. The fact that the idea that we can't get it all in one place is ludicrous, because at the alkaline vent, tell me what you can't get at the alkaline vent. You can get all the metals you want, and of course we live off metals. We still go to the pharmacy for metals, so they are all important. It's the inorganic elements that bring organic chemistry to life, after all. So we need the inorganic elements. They're all there at the vent. The phosphate's there. There's another paper came out a week ago showing just how much phosphate there was in the early ocean, orders of magnitude more than people used to say, because they said, oh, there wasn't enough phosphate in the vent, near the vents, but that's been shown to be true, wrong. I mean, things are happening so fast now in different areas of science. So I think that Orgel is just simply kind of yesterday's news, and no challenge to the present work on emergence of life.
Continuing on with Dr. Stephen Benner, and I know that you have a slide on this. Let me try to hunt to see what's going on here. So you have this slide, and before we get to Benner, if you'd like to talk a bit about what you intended with this slide before we get to his emphasis on the water paradox.
Okay, so my wife tells me that I should try and get an equation, and then people might believe me. Well, it's just the emergence of life is too complicated for a single equation like E equals mc squared. And I'm afraid to say this is my equation, and we've updated it since. But basically what you've got here is to showing that you've got all the materials that you need to go back to that last question. You've got carbon dioxide, which is bubbling up, by the way, from the sea bottom through volcanoes and cracks in the crust. You've got nitrogen, water, of course, in the ocean. You've got hydrogen sulfide, hydrogen coming up in the vents, methane coming up in the vents. They're alkalines, and it's coming into carbonic acid ocean. So the CO2 makes a a fluid very much like a popular drink, a bubbly drink, acidic, of course, bad for your teeth. So you've got an acidic ocean, you've got an alkaline vent, so you've got this disequilibrium. You might just be able to see pH units of about a difference of 5 there. That shows you've got at least 200 millivolts to be able to generate the first organic molecules. You also have the proof, I think, that there was no problem in having iron oxides and materials such as that, fuggerite, green rust, and so on, because the banded iron formations are the oldest sediments or precipitates in the world, our banded iron formations, and that's what makes our world go round. We're still in the Iron Age, and we use these very ancient iron formations for our iron in our present-day Iron Age to still make the railways and so forth that we're making today. So there's no problem about the source of absolutely, I would challenge anybody to find what's missing in the system in terms of source. Now, of course, he went on to say, Benner would go on to say, well, what about the RNA? Well, you have to build things from the bottom up. There's this very nice point in Gulliver Travels, whereby the architect in Gulliver's Travels decides the best way to build a building is to build the roof first so that the workers can work in the shade from the sun or out of the rain and so forth, and they build the foundations last. Well, of course, that's what the RNA world is doing. They have a roof, the RNA, incredibly complex and very rather weak molecule. How you can't make that from scratch. You've got that's like making the roof first. You can't do that. You've got to make the foundations first. So you've got to make the amino acids first. You've got to make the peptides first, and so on. You've got to make the enzymes before, or some of the enzymes before anything like RNA and DNA can come into the picture and be generated in that system. So, and I think that, frankly, most of these people privately know that, but somehow or other they're riding this tiger, whereby, and they can't get off it, the RNA world. Now, the RNA world, if I can get to this point, is that you look at this picture right in front of you, and if you take these arrows, the green and the red arrows, you can actually put them right down to the membrane, to this kind of red surround, to the to the mound. In other words, you get a very, very large gradient across here. But if this were a pool or a lake, and this RNA, shall we say, raining down in asteroids, what would happen to it? It wouldn't get concentrated. And anyway, you've got to keep on producing it. You can't just get RNA from asteroids. You've got to make it yourself. Everybody knows that, for example, modern factories need to have their suppliers right close by because they need things just in time. And they've got this electronic way of getting information out of what they're running short of so they can get the materials in just in time. Well, you can't get RNA just in time from a meteorite, which rarely has anything like RNA in it anyway. So, I just think that whole idea is ludicrous, and it fails the Schrödinger test of the entropy requirement, which is a low entropy environment, that there's no order to one of these warm little pools. Now, can I just point out that the Hadean is very well called. Now, the Hadean is the world between 4 billion and 4.5 billion years old. Hadean means hellish. It was hellish. The day lasted 12 hours. The moon was only 30% of the distance away as now. The number of days in the year, therefore, was something like 800, and therefore the actual lunar month lasted 12 Hadean days, or 6 of our days. So in other words, the moon is whistling around the Earth so fast, and it's pulling the waters with it. And of course, you're getting these hurricanes, and I think one of the difficulties of most people who never looked out the window is that they assume that everything was always rather like it is today. It's only when you get something like Hurricane Ian that people start looking out the window and thinking, well, that's quite a hurricane. Well, that was the nature of the early Earth, hurricane with no Florida to stop it, that would just go round and round and round with huge waves, tsunamis, large tsunamis going right across what would be the North America, just like the Chicxulub crater polide had that effect. So the idea of a warm little pond, RNA pond, to my mind is ludicrous. It's absolutely unsupportable. And I think that a lot of people must know that, but they cannot bear to give it up. But I think that the days of the RNA warm little pond, and I think we can call it the RNA pond these days instead of the RNA world, the RNA pond days are limited and over.
I'm happy that you mentioned Florida stumping Hurricane Ian. One of my next questions is going to be getting into your critique of the existence of land in the Hadean. Before we go there, I want to get into a little bit more on the water paradox. And I have a quotation here from Dr. Benner. So let's see. He writes, "The syllogism that generates the water paradox goes like this. 1, RNA can only operate in water. 2, RNA cannot be formed in water. 3, therefore RNA cannot form in the only solvent where it can operate." He continues, "The premises actually have strong scientific grounding. RNA has a repeating charge in its backbone. Therefore, it dissolves easily in water and pretty much nothing else. Further, that repeating backbone charge is essential to its ability to support Darwinian evolution. So RNA can work only in water. So why can RNA not be formed in water? Briefly, because many of the chemical bonds that hold RNA together are unstable in water. They fall apart. Indeed, as you're reading this paragraph, these bonds are being broken in the RNA in your body because, as we know from Star Trek, we are all, quote, ugly bags of mostly water, unquote. Fortunately, you have evolved for aeons to repair the bonds in your RNA and DNA that are broken by water." So Dr. Russell, could you get into a bit more on the water paradox? And I know you have a slide on this.
Yes, it's not, yeah, keep going, I think. Oh, that'll maybe that'll, well, any of these, well, there's a good example. Well, I can't believe, I thought that Steve Benner was intelligent. He can't really believe this. The whole point is that RNA is made in cells, in water, but the point about the water in cells is they're not a bag of water. The water, what is structural, it's all part of the system. It's not wet water, it's just water in the system. And so, for example, on the bottom right here, in our Fuggerite, this is our mineral, you can see water molecules, 1 or 2 deep within those layers. So there's absolutely no problem about having small amounts of water, just the right amount, because you need it to make RNA, actually, and you need it for operations of RNA. And here's some water problems where, well, as I say, people aren't looking out the window, because here's some structures you can see, for example, top right, you can see these in all the crystal shops, these beautiful septuagenarian nodules. And what are they? They are clays that have dried out below the water table, giving you those cracks, and the water comes in to replace with calcium carbonate or iron or something like that. And here are some actual mud cracks found on the sea floor. So and the mind boggles that these people have no idea of any geology. You know, there's a whole discipline out there called geology, and they have no inkling about it. Now, my job is to learn as much as I can about biochemistry, thermodynamics, and so forth. And I admit my ignorance, but geez, I'm learning. I'm trying to learn. They should take a step back and learn something about geology, but somehow or other, it's a dirty subject, so people don't bother.
And so, with respect to the water paradox, there are various approaches that have been taken. The idea of, how cells go about it in terms of mechanism of molecular crowding to protect from and to facilitate the proper situation in terms of thermodynamics for condensation reactions in water, the reduction of water activity under confinement, and also wet-dry cycles. And so you usually talk about the layered nature of Fuggerite. And so can you speak a little bit about the water content within the Fuggerite layers?
There's nearly as much water in Fuggerite as there is in an enzyme. So the water, basically it's bound water. You started this question with something just slightly different about that. How did you start that question?
In terms of the different approaches that have been used to kind of circumvent the water paradox, you know, in terms of like, yes.
But there is no water paradox. You're looking at a slide showing there is no such thing as a water paradox. It's a made up idea in support of the RNA world. Now, and I'm told, right, can I just, so because I can't get onto my website right now, I've just got a paper coming in here and I've got it on my telephone, and it's called Abiotic Synthesis and Chain Extension of Unique Peptide Isomers, and it's made in water, and it's just come out by Professor Graham Cooks, and it's in the Proceedings of the National Academy of Science, and I think we have 3 or 4 references to Russell et al. In it. So the idea that peptides can't be made in water and so forth, it's all just bunkum.
Very well. So there will be a couple of follow-up questions that I have there tangentially related to this, but I'd like to move on to your critique of the idea of there being land during the Hadean Aeon. And so there was an article written by Junkar Naga that was published as a rejoinder to your article, The Water Problem, Sick. And in his rebuttal, he writes the following, quote, for the notion of the mushy Hadean surface, Dr. Russell cites the work of Montu et al., which advocates a prolonged greater than 500 million years duration of magma ocean solidification. This work is problematic in at least 2 major aspects. First, their melting model is based on the experimental study of Andrault et al., which has recently been suggested to be grossly in conflict with other experimental data. Second, their cooling model does not take into account the role of the Rayleigh-Taylor instability, which can efficiently cool down a solidifying magma ocean, unquote. So what do you make of the response from Dr. Koranaga on the possibility of land during the Hadean?
Well, I wonder what his motivations are, because he's come out with papers since that seem to support the alkaline vent model. So, and if I could go to a slide, I've got a good slide there by Palin. Perhaps you could find that.
Is it before or after? Do you know? I'll start.
I think keep going. Keep going. I've got a feeling more. All
right, so let's go the other way and see. There we go.
There it is. So here's Palin. Okay, so this is 2020, secular change in the onset of plate tectonics. So this is the first 500 million years you're looking at. And the point here is that here's a mantle plume coming up, which is, everybody agrees, makes things like Hawaii and the Java, the Ongtong Java Plateau and so forth. And it makes these big structures like Hawaii. But in those days, here's the plume. It was much hotter. The mantle was much hotter in that time. And this is Palin's idea, and points out that it's not just a matter of whether there's an ocean, what's called a magma ocean or not. It's a question of the fact that the mantle plume itself is so low in viscosity that it can't support these ocean plateaus. And if you go, so there's one plateau today which is really extraordinary on the Earth. It's called the Ongtong Java Plateau. It takes up 1% of the Earth's surface, so it is gigantic. And yet its natural height is 2 kilometers beneath the sea floor, even to this day. So the idea there was land, to my mind, in those days was ludicrous. There was just no continents in the first part of the Hadean or middle part of the Hadean. And if they were, it would just get washed away by all these hurricanes and tsunamis and so forth. And the fact that you've got such high tides, you know, you can't have a nice little wet, dry cycle when you're looking at kind of pools on the modern Earth. It's just not. It's not realistic geologically to think in the same way. Well, yes, you can hear I'm lost for words, and I think it's only a matter of time before this is conceded.
Now, with respect to the wet-dry cycles, you know, we're talking about a criticism of the hot spring hypothesis, but several advocates of alkaline hydrothermal vents, particularly a paper published in, I believe, 2018 by Nascimento Vieira et al. I believe Bill Martin is a co-author on this paper, Martina Prainer and others. And what they emphasize is the idea of serpentinization acting as a kind of wet-dry cycle, leaching up the water as minerals precipitate in a kind of cyclic process. And I was interested to get your opinion about what you make about that comparison. Do you think that that's a legitimate comparison to make, or do you think that comparing serpentinization to wet-dry cycling is problematic in some aspect?
So in 15 years at NASA, I managed to complete 2 serpentinite experiments, and I say it took that long because it's that difficult to make. We made the reactors from scratch from our own design, and there were serpentinization reactors, and they made formate, acetate. The kind of expectations were fulfilled. They made very tiny amounts of methane, much less than anybody ever expected, and very little else. So to my mind, serpentinization is something that produces the fuel. It gives you the electrons in the form of hydrogen and perhaps a bit of methane, but that's it. And you've got to be able to have something that can be self-sufficient. It's got to be able to make its own way in the world, so to speak, as a cell. And I don't see how you can start in the middle of a serpentinite and turn yourself, especially without the proton motive force, because that would be missing, into a cell. So to my mind, this was this is an interesting paper that showed the possibilities of chemistry, but it had no relevance to making the first cell, because it simply avoids the fact that you need free energy for organization. You can do all these experiments and you can make all these beautiful molecules, admittedly not easy to make RNA, but all the other ones you can make very easily in the lab now, and have been doing since 200 years ago. But none of them have actually turned themselves into a cell. It's just chemistry on the bench. It's no good. It's got to be a kind of geochemistry that can easily segue into a biochemistry. And to my mind, what's missing is geology and physics. People aren't realizing that much of the problems of life are about physics, just like the rest of the universe. One of the things I always like to say about to a child who's 2 or an adult, whatever walk of life, you've got to get the physics right. Whatever you do in life, you've got to get the physics right. You've got to know how to cross the road. You've got to know how to drive. And you've got to get the physics right if you want to do something like the emergence of life, because it's basically physics.
Very well. So emphasizing what serpentinization is able to produce. So, you have an earlier paper on serpentinization as an energy source for the emergence of life. And I've watched you in some interviews talking about not having much success in terms of your approach there. So as it stands now, you would basically say that serpentinization, I guess you would still consider it like the mother engine of life in terms of its production of these vents, but you don't envision synthesis taking place within the serpentinizing cracks of these vents, with perhaps like wet-dry cycles facilitating it, perhaps like the reduction of nitrate by green rust within the serpentinizing cracks, leading to the synthesis of any kind of organic molecules.
So if you're doing something really, so the emergence of life research is in the too hard basket. But of course, people don't want to realize it's in the too hard basket, so they think it can't be that hard, although most people realize it is hard, but not just how very hard it is. So I understand a lot of different research points of view, and the point is for a scientist such as myself to hold a strong, bold opinion, because only then can it be attacked. And the whole point is, unlike the RNA pond, you can attack the alkaline vent, and it has made a difference to the way we think about the alkaline vent, and we have had to negotiate our way, so to speak, into finding different solutions to the ones we first started out. Now, we just haven't given up on the hypothesis yet, but that is natural. And to have a bold hypothesis, I'm not ashamed of the bold hypothesis, but the thing about being bold is you've got to stick to your guns. You can't just say, well, now I think that might be something entirely different. No, we think it's the alkaline vent and we think it's serpentinization. We're absolutely fine with that. But quite how it worked is certainly in our minds different to 33 years ago when we first had the idea, or 35 years ago.
Okay.
Of course it is. That's the village.
So I wanted to give you a little bit of an opportunity to respond to some alternative models. You've given some pretty forceful criticisms of the hot spring view. They've tried to harmonize their perspective with thermodynamics, and so there is a quote from Dr. Jackson and a quote from Dr. Deamer that I would like to share. And I do apologize. These quotes are a little bit lengthy. So if you would please bear with me, I will get through them as quickly as I can. But I think that actually, you know what, the much more interesting one comes from Dr. Deamer. And so I think we've talked enough about Jackson, and I'll just give the Deamer quote. So he writes the following. The molecular crowding that develops with evaporation and the growth of solute concentrations elicit both a Raoult's law, excuse me for mispronouncing that, a Raoult's law decline in the activity of water and a growth of solute activities to values that can exceed their molar concentrations by orders of magnitude. The latter can be critical in evaporative settings where activity coefficients, reflections of deviations from Henry's law, can grow increasingly sensitive to solvation differences among solutes. The activity fraction thus falls strongly with evaporation, and at some point, oligomer growth becomes exergonic. Indeed, increasingly so with oligomer growth, and large complex oligomeric products are the result. He continues, by increasingly downshifting configurational freedom to a more confining volume that progressively tends to a two-dimensional space, evaporation and a mounting air-water interface overturn otherwise unfavorable anti-entropic factors and inverts Gibbs energies to favor condensation. It is worth noting further that folding, an inherently anti-entropic process, is similarly advanced by molecular crowding. This rationale can be enhanced to the limiting case at the interface itself, where the loss of a full degree of freedom can then promote assembly and molecular organization through the formation of Langmuir monolayers. Significantly, and in contrast to the commonly presumed random oligomer assembly, this scenario leads to a thermodynamics-governed prebiotic molecule synthesis, the potential advantages of which have been discussed. So any response to
I certainly will respond to that. I mean, I can't stop myself responding to that. It's very interesting that he's now picked up the language we've been using for the last 10 or 15 years, almost word for word type of language, except he doesn't understand far from equilibrium thermodynamics. Let me just put one major point to his idea, and that is, do you see anything about wet drying cycles in the evolutionary tree at any level? They are just not there. So the idea that evolution is a continuum is not held by these people. They think it was a wet-dry cycle and autocatalysis to start with, and then it suddenly magically turned into having proton gradients and redox situations and so forth. Well, actually, they were started that way, not by wet-dry cycling, and you wouldn't get wet-dry cycling in the Hadean anyway. I mean, it is and as I say, that now you think of Hurricane Ian is just reminding us of what the world can do even now. But imagine what it was like in the Hadean. When, by the way, the UV radiation was 10 to 100 times what it is today, let alone all the other difficulties of that idea. So that's not very good for life, as we know when we sunburn ourselves on the beach.
Very well. So there is a concern here that I wanted to talk about with respect to how you approach the concentration of what's synthesized in the vents. And I have some notes here about this, but off the cuff, I wanted to ask you about the dilution problem. And so the notion of Venturi pull, of oceanic water infiltrating the vent. So people usually talk about like the membrane and the ocean side versus the alkaline side. But I've noticed in several articles that what they actually mean by the ocean side is actually just the ocean water within the vent system. Is that how you approach this?
No, it depends on the system, but an alkaline vent is mainly, almost entirely, the alkaline vent coming from the alkaline fluids, hot fluids coming from depth, having been altered during serpentinization. So that is quite different to the outside ocean. And it's very similar to a cell, by the way, alkaline inside and somewhat acidic on the outside. So our system actually has the proton motive force in as part of the history. Unlike the wet-dry cycling, there's no wet-dry cycling in the history of evolution, but there sure is the proton motive force everywhere. So to my mind, that kind of discharges those criticisms. I might have missed something. The Venturi effect, by the way, we came out, I mean, you can find all this work in our literature from 10, 15, 20 years ago, on 20 more, 30 years ago, on Venturi effect and so forth, bringing in fluid from the outside. But of course, what we're doing is we're bringing it in those thin nano layers in the green rusts. So this is not flooding in like a hole in a dike in Holland. This is just very fine, highly low entropy water coming in through very fine interlayers in crystals and mixing, if you like, with the alkaline fluid. And as I say, that you've got to realize that water in those interlayers is 2 molecules or 3 at most molecules deep. So of course we had crowding right at the beginning. And we have no problem with crowding. We have crowding immediately. We don't have to wet-dry cycle to get crowding.
And with respect to concentration, initially you were pretty optimistic about thermophoresis, the production of a flow instigated by the heat source of the H2S, pushing away the synthesized molecules toward the colder regions of these vents. Since then, from what I've understood, you've moved away from that. And so I wanted to ask, in 2009, for example, Budin and Szostak discovered that salt content negatively impacts the concentrating ability of thermophoresis. Is this one of the primary reasons why you moved away from this mechanism?
That isn't one of the reasons, but it was very interesting that they did that experiment with having referenced one of our papers, mainly by Dieter Braun at the time. But no, I think that the thermal contrast across a very fine chemical garden just isn't enough to drive thermophoresis to my mind. And you could say there's natural electrophoresis and so forth that can happen instead, and other kind of gravitational differences within one of those very fine vents. So I think it was a very interesting approach. And I think that some people still find it to be very attractive. I don't, but on the other hand, I'm not saying it's wrong.
Okay.
It's not useful for us. That's all I'm saying.
And I noticed in one of your more recent papers talking about the unavailability of fresh water during the Hadean, there have been some papers that I've found that suggested that the ocean actually had a much more reduced salt concentration. The particular paper, the title of it, I can't remember off the top of my head, but its conclusion came to the idea that the Hadean Ocean was far more carbonic, but also far less salty. So what is it that you feel, like, how does it work in terms of salt content in the Hadean Ocean? And especially, for somebody like myself who tends to like thermophoresis, if we only have a water world, I would have to abandon thermophoresis in terms of salt concentrations in the ocean. So why do you regard it as particularly high during the Hadean, salt concentrations in the ocein?
One argument from the present day is, of course, you put all the salt in alkaline lakes and so forth back into the ocean, then you've got, shall we say, twice as much salt in the ocean. But if you think about the very first vapors that came off the cooling Earth, a lot of them would have been chloride, and probably some sodium chloride vapor. Now that's got to go somewhere, and it probably was rained out into the ocean. So I suspect that the early ocean was relatively salty, but it was also much more magnesium rich than it is today, and probably calcium rich. So I think there's no problem about having salts of different types. So I certainly wouldn't think it's anywhere near fresh water. I mean, in fact, it would be, well, it beggars belief that it would be fresh water to me.
Okay. Our next one here is on amyloids for membranes versus Fischer-Tropsch synthesis. And when I went through the literature, I found a lot of perks, so to speak, of having a lipid membrane. However, you and I believe Dr. Duvall on the article on Fujirite, the not so simple progenitor of the first cells, emphasize peptides first as a membrane. And you emphasize that it's kind of expensive to get this kind of Fischer-Tropsch synthesis. So my questions here are, why are you convinced that amphiphilic vesicles are absent at emergence? And you refer to them as costly. Just how costly are they to produce?
Well, can I go back to your middle point here? And that is the Fischer-Tropsch reaction is nothing that you could put into a cell. So it's inappropriate. It's high temperature, high pressure system. So I think so you can't make that analogy. One of the things I'd point out is that what do lipids do? They make things soft and slidey, and they also make part of the membrane. They make about 30% of the membrane these days. 70% of the membrane is made by peptides and protein. So the idea in most of the books that you see one little enzyme stuck amongst this huge sea of lipids is quite wrong. So the textbooks have got a lot to be blamed for here. They're just plain wrong. The other point is that if you can imagine in a world of, you can imagine a social world like ours. What do you do if there's nothing to do? If you can't do anything, what do you do? So lipids can't do anything. Peptides and amyloidal peptides can do things. They can sequester copper and cobalt and nickel and iron and so forth, and phosphate. They can actually take it in. They can do a job with it. But lipids can't do anything. They're just kind of neutral, and they're kind of hanging around. But so in other words, why would evolution, to start with, say, let's keep making lipids when it couldn't? They're not doing anything. I think everything, as in life, has to pay its way. And the lipids couldn't pay their way until till a really sophisticated cell got going. And you've probably seen papers with mine and Bill Martin pointing out that it looks like the lipids being different in the archaea and even different chirality in archaea and bacteria is a suggestion that, in fact, the lipids are late in evolutionary terms. It's just that they make everybody satisfied if they happen to come from the microbiology or biology, because they've always dealt with lipids. But that doesn't mean to say they were on the early Earth.
And the membrane transport using an amyloid membrane, you guys emphasize that gaseous nutrients can get in, small particulates can get out, and that waste is filtered through the system naturally and percolated out into the ocean. Why do you feel confident that the waste would be percolated out by flow? And can you give us? Yes.
Yeah. Okay. Good question. So the waste is what is the uncooperative material. Okay, so it's just like you'd expect. Anything that's uncooperative or not useful, like our day-to-day life, one discards. Now, if it's not useful, it probably means it's not charged. It probably is neither negative nor positive. So it can kind of float away, a bit like the early lipids probably. If you made any, they would just be part of the waste product because they're not pulling their weight. They're not doing anything. You've got to have stuff around that does things, does stuff. So that's the waste. And the waste just gets discharged. It's not doing anything for us.
Okay. And my next question has to do with Palladium. Harpreet Kaur has recently done some really interesting work using Palladium as a catalyst. And I also know that you have a slide somewhere here on this. And rest assured that as we kind of skip through these slides, I'm going to return to them so that way you can comment on each one, because I know, I mean, you put these slides together for a reason. I want you to be able to cover what you want to talk about with them. This is the one that you have for Palladium. And so my question is your thoughts on the plausibility of Palladium contributing to the emergence of life at alkaline vents.
It's got to be available. So it's just frankly 1 part per billion. When you've got 10% iron, what's the difference between that? You know, it's orders and orders and orders of magnitude difference. Well, iron can do a lot of jobs, and nickel can do a lot of jobs, and palladium can do it, of course, but there's hardly any of it. So you wouldn't be able to get hold of it. It would be too expensive, so to speak. Well, not expensive. It would just be a rarity. And we'd say that, in fact, one of our papers actually quotes the point that green rust acts as a poor man's palladium.
Could you explain that a little bit more? In what respect?
Well, because, you know, of course, we'd all like to have gold watches or whatever the great thing is these days, but not everybody can have, shall we say, a Lamborghini car or some such. There's only just a few cars, you know, for the world's population, so that there's just not enough to go round. And so there wouldn't have been enough to go round. And don't forget, much of life would have failed. Much of early life would have failed. So you're just looking at survivors. So all the time you've got a failure, you've wasted the palladium. So there just isn't enough of it. So it was no help to life. It had to have something that was very readily available. So what can I say? You know, like, you know, plastic is relative, is so available. So of course we would all like to have leather bags and so forth, but there's so much plastic. We all use plastic because it's so easy to get hold of.
Speaking of availability, a article published by, I believe her name is Maria Colin Garcia in 2016, Prebiotic Chemistry. I think, I can't remember the title, I apologize off the top of my head, but Alkaline Vents and Prebiotic Chemistry Review, discussing the possibility of using hydrogen cyanide at alkaline vents for synthesis. I believe this is the next slide. So for people who are considering that route for synthesis, what kind of advice would you give them?
Well, be careful, because hydrogen cyanide's a poison, as we must know. So all those books on detective novels and so forth, they all tell you what a poison it is. It's a poison to things like the ferredoxins, that and all the oh God, what are they? Anyway, different redox enzymes. This poisons them. So the idea that you start with hydrogen cyanide seems thoroughly ridiculous. And as a geologist, I know that it wasn't available anyway. So it's just these people, they're chemists, and they're reaching out for something to make something. But it doesn't mean to say that's how things happened. And to my mind, they certainly didn't happen. That's why I left this slide blank.
Would you also describe formamide in the same way? Would you regard it as toxic for those pursuing that route for synthesis of things like RNA?
You can't start with it. It would be too unstable at the vent. So it's something, and it's actually hard to make in terms of the thermodynamics of it. So I think, yes, I think those ideas of having a nice little pond with formamide or formaldehyde in it is just nonsense. And anybody who's been out in the world looking at different lakes and oceans and hot springs and volcanoes would come to the same conclusions.
And for example, there's the Hudson paper that you referenced earlier. They make a brief reference to the idea of formate and ammonium upon heating, yielding formamide. So to that approach, you would suggest that the thermodynamics is still not feasible for that kind of reaction to take place?
I think by the time you get to making something comparable to formamide or formaldehyde, then you actually have to have it coddled within a peptide or a small protein, so to speak. So it's got to be itself. It can't be just part of the body fluid, so to speak. So that was my point, that you can, of course, yes, you can keep these. I mean, a lot of life, as you very well know, it's kind of lives on a high wire. It's very unstable. So how does life stabilize itself? It wraps itself up in peptides and proteins and so forth, and of course cells. So I don't like to talk about the kind of chemicals that the chemists deal with at the bench. This is the chemistry bench is not an analog for the Hadean Earth.
So we have to turn now to phosphate and the first phosphorylating reactions. Dr. Wimmer in 2021, discussing the role of pyrophosphate and other possible energy currencies at the origin of life, insisted that pyrophosphate isn't used as a currency, but it is used to lock in reactions. And I've heard you suggest in previous interviews that the conversation on phosphate is extremely confused. So my question to you is, how do you approach these different kinds of energy currencies, methyl thioacetate, acetyl phosphate, and pyrophosphate, and how do you envisage the role of phosphate at the emergence of life?
Well, one thing I've just said is that there used to be somebody who thought that there was no phosphate on the early Earth, so you had to get it from something called struvite from meteorites. Now that is now looking ludicrous because there's a paper just came out, I think in Nature, but I'm not sure, but it's only in the last 2 or 3 weeks, showing the amount of phosphate in the early oceans was likely orders of magnitude higher than ever realized. So there was no problem for the source of phosphate. And actually we've known that since a paper in 1993 by Yamagata, who showed that P4010, pyrophosphate comes out of volcanoes in quite large amounts. So there's no problem about the origin of phosphate. I quite admit that there are problems about how to put it to use. Now, my own view, well, let's put it another way. Of course, yes, acetyl phosphate seems a very good way to get started. But pyrophosphate is also as an energy molecule. But of course, don't forget, and I'm not sure how they use this, but one of the people think of it as an energy molecule, but actually one of the things what ATP does is that it actually blocks the back reaction. Do you remember I was talking about the roller coaster and how you need this click, click, click up? Well, the click, click, click in things like myosin and kinesin and so on is done by hydrolyzing ATP to ADP to stop the back reaction. So it's very, very similar to a kind of, so you think of it as an energy reaction, but it's not really an energy reaction. It's a backstop reaction. It's stopping things going back. So, and certainly pyrophosphate could do that just as well probably as ATP. So it's about hydrolyzing the phosphate bond and not using it necessarily to make molecules join up. Everybody thinks it's all about making molecules join up. Well, of course, it does take part in that, but it's not just that, and certainly not quite a large part of it. So I thought it was an interesting paper on the way to trying to understand what's going on, but it's not a classic, I don't think.
And with methyl thioacetate, worked on by researchers like Kitadai, you emphasized to me in previous conversation that there are major differences in your approaches, and you described his vents as different from yours. Could you briefly touch on the differences between your approach and Dr. Kitadai's?
Well, ours are all within structures of some kind. So in other words, they're kind of protocell structures or in interlayers within crystals. His are out there on the side of the volcano. And of course, I think that then you have a water problem. So that's where the water problem people can come in and fair enough criticize Kitadai, I would say. But they can't criticize us because we have very, very low water activities.
Okay. Is there any role for carbon monoxide in your approach?
It's normally a poison. You can make it, but you need to make it to order. So it's all this stuff. That's why chemistry is no use to my mind, just thinking about chemistry, because it's got to be made to order and in a particular package. or it's got to have a particular holder. You know, you can't just have the front, you can't just have the axe without the handle. All these structures that are active must have a handle of some kind, or something, a safety structure to stop them going wild. So to me, that's why chemistry and the idea of the autocatalytic networks and all that, to me, is hopeless, because chemistry would not behave itself. It has to be contained at every level.
My last question for you, and after I ask this, we're going to go through your slide presentation just to make sure that you're able to say what you want to say about each one of these slides before we end. But my last question has to do with Hadean CO2 levels. There's a paper published by Kadoya, Chrysanthemtoin et al. In 2019, arguing that impact ejecta weathering will shuttle a great deal of the CO2 out of the Hadean atmosphere. And they envisage something like a snowball Earth with low levels of CO2. And so I'd like to get your response to the Kadoya paper. I know you've referenced Lupton to me, which is extremely helpful. If you could explain your response for anybody who would view this program.
Well, of course, there are a lot of unknowns. It's quite true about the early Earth. But what we do know is that CO2 is bubbling out of the bottom of our ocean even today. And you can find it in what are called popping rocks, which are basalt lavas that actually contain carbon dioxide. So carbon dioxide is continually being fed to the ocean from the base. And we know that too from looking at lakes in West Africa, where the amount of carbon dioxide is gives it something like 10% CO2, as I recall, at the bottom, which gives you a pH of 5.1, acidic, carbonic acid ocean. Venus, our sister planet, has 90 bars of carbon dioxide. It would be very hard to take all the carbon dioxide out off the planet with a few meteorites, even however big they were, because it just keeps on streaming. And one of the things is that everybody thinks it's all about the atmosphere. No, it's about bubbling from the bottom, because if you put the carbon dioxide in the bottom, then of course it's dense, it's pretty dense. You can even have fluid CO2 itself, just lying there as a different phase. So the idea of getting rid of CO2, to my mind, is ridiculous. And here, thank you for putting this slide on. This is a good example. Lake Nyos, Cameroon, definitely worth reading about, because this is where a great chunk of CO2 came out and killed all the animals and villages around Lake Nyos. And this is a worry around some of the lakes in West Africa. And you can see on the right-hand side, Kusakabi has shown that you get right down to the bottom of that lake, even after the loss of the CO2, and you're down around about pH 5.1. So you've got an acidic, carbonic sea right down there, just about 100 meters. So that's absolutely no problem at all. And the whole Earth would have been like that. So I really think that they're clutching at straws, frankly.
Very well. Thank you very much, Dr. Russell. You've answered all my questions, and I really appreciate the generosity of your time. I want to go through some of these slides just to make sure that if there's anything that you want to cover about them, you put in work here to put these slides together, and I want you to have the opportunity to present the information that you wanted to with respect to them. So as we go through, if there's anything additional that you'd like to cover with respect to them, please have at it.
Well, okay, let's do it quickly, because I don't, I think the talk's over. One thing I would say, any people in your audience that would like any particular question answered about any of these slides, they can always email me. I can send them stuff by email. So, maybe that could be it. I think it gets too complicated, really. Let people ask a particular question on email and or even through your good officers, and let's do it that way. How do you start there? These are membranes made of these peptides, by the way. These are natural peptides. So I think that's quite easy to get membranes with peptides, not lipids. And the peptides, as you recall, can do things. So yeah, okay, go through the slides and you got me.
All right, this is your work with Duval.
Go back one. Well, oh, sorry, did I miss one? One more back. Is there one more back? So one more before that. I think I got, oh, maybe not.
Okay, let's go in the
right,
other
okay,
direction.
go forward. Yeah. Well, this is how we see the first cells. Well, this is the green rust. So this is kind of, it's a sketch, okay? But the point is, there's the ocean on the left-hand side, and the vent, the hydrothermal alkaline fluid on the right. And I've made a sketch of it, putting a green rust or fuggerite in between, and you can see there's interlayers, and the green and the red are different states of iron, whether they're iron oxidized or iron reduced. And we know for fact that if you put in nitrate to the systems, they will, within a day, to generate ammonia. And possibly, we're not sure, but maybe hydrazine. We like to think we're going to make methane that way. And we can certainly make, from the ammonia we made here, we can add that to something like called pyruvite, which is a carboxylic acid, and we can make alanine. We haven't made polyalanine yet, although people have made dialanine. So, below this, you can see how if you make a short peptide, then you can cosset or protect these things like the iron sulfides and the phosphates and the individual nickel ions and so forth. So that's what I mean about, it's not just chemistry. You need to actually have these things wrapped up, otherwise they'll cause havoc or just lose their ability to do anything. So you've got to have these things at the nano scale to be able to do stuff. Yep.
Tronic.
Oh yeah, I do like the one with Galileo. Now, we just forgot all this. You know, this is a fantastic work by Galvani and Volta, and it's actually a kind of tragedy for Galvani, a real tragedy. But basically, he did show that the frog's leg moved with lightning, with electrons, and the frog's leg is a lever. You know, it's a mechanical engine. And there they were in 1792, pointing out how life worked. And Volta went on to invent the battery from this incredible work. I mean, it's just astounding work. And just to remind us that even today, the E. coli uses 10 to the million electrons a second, and 110 minutes can take complete random material and make another E. coli. Isn't that fantastic? And these people, and even Volta was first to understand methanogens. So these people were just forgotten. Anybody who's, I know you are, Drayce, that you're interested in the scholarship. You know, I'm always pleading with my students, get to the scholarship, get to the first papers, because those first papers really wanted you to understand what they were doing. Of course, they've been made into history now, but nevertheless, having a sense of what they did is really worthwhile. And this is a fantastic piece of work by Galvani and Volta, who didn't get on, by the way. But nevertheless, between them, they gave something that was independent of their personalities.
Continue. And I think most of the others, let's see. Is there anything here, Dr. Russell?
I think it's too complicated to talk about, but this is where we would make pyrophosphate or acetylphosphate within these interlayers in green rust. And we would point out that's down below on the left-hand side, the ferric green rust is putative proton hydrogen pyrophosphatase or proton pyrophosphatase. And above is actually how a proton pyrophosphatase actually works. It's not like an ATPase. It's got some things in common, but it's just basically like, what can we say? It's just a pump, or what do you think? What those things that pump you use to get fires going? You know, you pump things. It's a pump, and you pump the protons in along with the phosphate, and you push them together, and they become pyrophosphate. And we think that would happen, and we haven't shown that yet. But we firmly think that experiments will show that's the case. By the way, I think it's fair to say, and as one might moan, is that, of course, this is the alkaline vent has been incredibly poorly supported by funding agencies, and most of the money has gone into the RNA world. I think I'll stop there.
Very well.
Okay. Thanks, Drayce.
Yes, and thank you as well, Dr. Russell. All right.
Okay. Be in
Oh,
touch.
I see. I see. We have somebody in chat here, Neslig. Neslig, I will get you in contact with Dr. Russell since he's open to answering.
Are they there talking?
Am I?
No, are they the people who are asking questions? Are they?
Yes. Well, they're in chat now, and they've been as we've been going through the slides. They had questions for us. There's
questions. Oh, fantastic!
Okay.
Right, I'll deal with it. Okay.
All right. Very well.
It might be next week. I've got a kind of heavy load right now, but next week.
Okay. Sure. All right. Yeah. He's got quite a number of questions. I'll also, since you did, kind of offer that people can get in contact with you. I will. I'll try to get Neslig in contact with you. He's actually another one who's very similar to me. Somebody who's very passionate about the idea of an alkaline vent emergence of life. I think both of you would really appreciate speaking with one another. So yes. Okay.
So will it be available online, or how can people access this in future?
Yes, this will be online. At first, it's going to be on my YouTube channel, but there are several other YouTube channels that I'm going to permit to share it. And I'll be sending you the link first to my YouTube channel's coverage of it. And then subsequently, when others start loading it onto their channels, I'll send you the link to those also.
Very nice. Thank you. I enjoyed that. Thank you for asking.
Yes, thank you. I appreciate it. Back at you, Dr. Russell. Thank you very much for your time today. I really appreciate it. And thank you very much for just a really great interview. So be well, and everybody out there.
The answers can't be better than the questions. The questions were very, very good. So thank you for that.
I appreciate you. All right. Well, with that, we're going to end this broadcast. Neslig, be sure that your questions will not be ignored. We will. I'll make sure that Dr. Russell is made cognizant of them, so you could get your questions answered. And everybody have a very good day. And one more time, thank you again, Russell, for a very good presentation. So with that, we will end.
Okay. Bye.